Hey, good morning, Ryan.
Morning.
Yeah, I hope you are not the only one today. Yeah, so Mariano cannot attend today's class. Um, uh, he completed the first rotation in my lab, and right now he's doing the second one. And today there's a lab meeting for him. So yeah. So Lloyd, so if you have time, so after the class, we can talk about the second rotation for you. Yeah.
Yes, I remember.
Sure. All right, let's wait for another minute. I think at least 2 other students are coming. I haven't received any notes from the other 2 students saying they cannot attend. But anyhow, I started recording the lecture. All right, so do you have any questions? Because we didn't have class last Thursday, and I posted some assignment practice for you. So do you have any questions about those practice assignment?
Not yet on my end.
Okay.
No.
Good. Yeah. All right. So today we're going to talk about the segregation analysis, which is related to the famous term, the mixture model. I already put some practice code, R code, for you to understand the segregation analysis. So if you have chance to look at that, so there's a like EM algorithm. So I write a small code to implement the EM algorithm, and I simulated a set of sample. After we talk about, so today I plan to complete this lecture, this chapter, and then if we have time, so I'm going to go through those practice code, and hopefully you can understand. So the theorem is kind of like advanced, so I don't require you to fully understand the stuff, but at least you know what is going on in the EM algorithm, and when and how we should use this method to solve what kind of like problem you may have in your research. So this is the key point. So let's get started. Okay. All right, segregation analysis. So in the previous chapters, we talk about how we can use a linear combination model to help us test any potential locus in a specific design, for example, the backcross design or F2 design. So here we suppose we use a F2 design. If you are interested in testing, for example, this locus, and this is a F2, so for any F2 population, any locus, we have 3 possible genotypes, right? So this, and this. And all right, so if we already knew the genotype at this locus for each individual in this population, then that's easy. So we can use the famous linear model, right? X equals to B0 plus B1 times Z. Z variable is the additive, right? And the B2 times the W variable, W genotype, which indicated the dominance effects. So this is the model, and we have already learned how we can estimate these parameters. So for example, the B1, which is the additive, right? And the B2, which is the dominance. And we can estimate this. And we can also estimate the variance of this estimation. And then we can construct some like word test or F test to help us test whether this additive effects or the dominance effects exist or not. So the existence of any non-zero, non-trivial effects will indicate the genetic association between this locus and the trait of interest. So this is the key point. All right, so we are very familiar with this. Then what if, like, for example, this if we have this kind of data, so we're expert now for testing the association between this locus and the phenotypes here, for example, the yield, the crop yield. However, if the situation is like this, so we're missing these genotypes. So we only observe the phenotypes in this F2 population, but we do not have money to sequence these individuals to get the genotype data for each of these locus SNPs. So what can we do? So in this very challenging situation, we can still use this linear combination model, but we use a slightly different advanced method to help us to separate. So here, actually, the phenotype you observed, the phenotypic value you observed for this population, F2 population, is a mixture, is a pool, right? Is a pool of several categories. Actually, we knew if this is a F2 population, and we knew this group of phenotypic values is actually a mixture of 3 subgroups or subpopulations. So we treat this kind of problem as a mixture model problem, because what you see for this composite population is actually a mixture of several subpopulations. Okay, this model actually applies to the F2 population, because in the F2 we have 3 underlying subgroups, right? Okay, so this is the typical data or the distribution we can see for a mixture model problem. So for example, if this is a F2, the classical F2 population, and if this represents the genotype like this, I use different color here. So if this represents the genotype like this, and if this is the mean, represent the genotype, the third genotype, okay? And each subgroup, actually, each genotype, if you check the distribution of the phenotype that is associated with that specific genotype, you're gonna see a normal distribution, right? So this is one normal distribution. This is another normal distribution, and so on. You do not, because they are, these 3 distributions are not far removed from each other, so you're going to see some overlap between them. So if you put them together, this will cause some like confusion or challenges, right? But with the mixture model analysis, we can clearly separate those 3 subpopulations. So this is what we're going to learn about for today. Okay.
Can you repeat that last part?
Say that again. I'm sorry.
Can you repeat that last part?
Okay. All right. So this is the challenge here, right? So the problem is like, if we do not know the genotype, but we only got the phenotypic data for this F2 population. So once we plot these values, so I'm going to show you in the practice exam, in the practice assignment, I simulated this kind of like population F2, and if we plot the distribution of this phenotypic value, so what we're going to get is something like this. So why not we just show, I'm going to show you the example I gave you, like, okay, in assignment, okay. So this is what you can see from the canvas, the newly uploaded practice code. So the first block of the code is to simulate the genotype Z, W, and the phenotype Y. So I hope you are clear. You're clear about like what Z, W, and Y mean, right? So Y here means the phenotypic value. For example, the height of the crop, for example. And if this, let's say, if this height trait is controlled by a, let's say, a causal locus, and for this locus, if this is a F2, so at this locus we have the additive effects. We use the Z to represent the three genotypes here, and we use W to represent the three genotypes that is associated with the dominance effects, right? Okay, so first we just simply generate 100 individuals here. So the probability for this F2 population is 1/4, 1/2, and 1/4 to represent three different genotypes, right? So yeah, I asked the computer to simulate this for me, so it's not too bad, the results. So out of this 100, we can see the genotype 1, there are like 23, so roughly like 25%, right? And for the last one, the 28, 25%. And in the middle, 49 is close to 50%. So that's good. The computer is always like doing great job if you can control your computer very well. And okay, so this is the X matrix. So the X matrix is actually, let me show you. So, okay. So if you use this block of code, you can generate the genotypes for this. So after you're done with this, this is the new X matrix, right? Genotype. So there are 3 columns for this X matrix. The first one is always 1. So that means like, that one means like intercept, the regression model, or we use the B0 as the intercept. Okay, now the Z variable. So the Z variable, I hope you remember, right? We talked about this. So when we look at the first one, the Z equals to 0 means what? Means this is the heterozygous individual, right? If this is a heterozygous individual, means A1, A2, then the dominance, the additive effects will be 0, but the dominant effect will be 1. So that's why you see the 0 and 1 here. That's for the first individual, the first row. And how about the second individual? The second individual, as we can see, the Z variable, equals to -1, which indicates the third genotype, which is A2, right? So if this is the case, the additive effects will be -1, but the dominance effect will gone. So because this is a homozygous individual, so you see 0 for the W variable. So and so on. So you can see this. So in this case, we can generate the genotype for this 100 individual in this F2 population. Now we can arbitrarily put values to the B, which is the coefficient. So we put the intercept as 10, and the additive effect A equals to 5. So if for the first, if for the first genotype, which is A1, so you're gonna add this 5 on the top of this intercept, right? Okay, now we put a very tiny like effect on the dominance effect. So we can treat this dominance effect equals to 0, a small one. So usually this one cannot be detected using the linear model. But we still put a little bit like effect here. So this is the parameter. All right, so now we can easily generate the Y, the phenotypic value by using this linear combination, right? Don't forget about add some noise here. So I use this random normal to put like some random noise to each of these individuals. I'm generating like 100 noise. This noise is normally distributed with the center equals to 0, but the variance equals to 1. So this is how we do this. All right, so once we got this, we're done with the simulation. Oops, sorry. We're done with the simulation. Right? Okay, so this is how Y looks like. So we have 100 Y values, right? But this is, so if you just look at these values, this is terrible. So you can get nothing. You cannot get any useful information out of this. Only if you plot this. So this is the plot density of Y. You're going to see the distribution of Y. So let me show you. So what do you see here? Is this something like what I just showed you in the lecture slides? Yeah, the mixture.
Yeah.
So that makes sense, right? Because so this clearly you can see like the entire distribution consists of like 3 subpopulations here. So this one is something like here, and this one is another normal distribution with center equals to 10, and you have the last one. So it's something here. All right, center like this. All right. Okay, then we can use what we're going to learn today, the mixture model, to help us to segregate these 3 underlying populations, right? So remember, this is F2 population. So that's why here I just generate this number of each categories which are following the F2 the F2 genotype frequency, right? So the first one is close to 25%. The third one is also 25% of the population, and this is roughly the 50% of those. All right, so it's fun. I mean, when I wrote this code over the weekend, it's fun to write those. Maybe right now it's a little bit difficult for you to write it, but it will be fun to read it and try it. I just wrote this code following the lecture notes. So if you implement those codes and see what you get from those code, then this probably can help you better understand the lecture we're gonna talk about. Yeah. Okay.
Thank you.
I'm sorry.
I said thank you.
Oh, you're very welcome. I'm happy like I can use some like example to assist me in teaching the lecture. Okay. All right, this is exactly what I'm talking about. So 3 genotypes, right? From the F2, and you're gonna see the mixture here. All right. So the idea, like the mixture model analysis, was raised by this scientist, the great scientist, the Fisher, and he actually used the iris flower as an example to introduce this idea. So what he did is like, so he studied, so there's like 3 different, this is not the F2 population, this is just like a natural collection. But for this natural collection, there are 3 subcategories of this flower. And if we just, at that time, I mean, back to then, they do not have like the advanced facility like us. So they cannot, they know there's a gene, but they don't know how to measure the gene, right? Sequencing. So at that time, the genotype information is totally blind to them. So, but what they can see is this, like, for example, some traits. Here, actually, he used like 2 traits here rather than 1, right? The petal length and the petal width. And if you just simply plot this this population using these two traits, and you can clearly see the segregation, right? And okay, then how can we like write a algorithm that can just use the value of these two traits to help us to determine, for example, so how can we determine the classification or for each individual? So for example, so how can we know this individual belongs to the second group? So we need an algorithm. So this is something Fisher developed, like using the mixture model analysis. So just based on the phenotypic value, we can still tell how many potential subgroups are there for this population, and we can also determine the classification or the class indication for each individual in this population. So this is the segregation analysis. All right. So for the most simplest example, if we assume the residual or noise is normally distributed, then we can use this mixture model setting here. So suppose this is a F2 population. So we knew at any locus we have 3 genotypes, which determine 3 subcategories, right? All right, and if this locus is following the Mendelian or the Hardy-Weinberg law, and we can assume that the proportion of these 3 genotypes equals to 1/4, 1/4, and 1/2, right? So that's the F2 feature. Okay. All right. Now, so we use K equals to 1 or 2 or 3 to represent the classification. So that's why you see K here, right? So if this individual come from the K category, then we can use this simple model to represent the phenotype like this, right? This is the mean of the subcategory where this individual belongs to. Any questions here? Is that clear? All right. And we plus a noise because this is the noise, right? So this is the expected phenotypic value for this individual if this individual comes from this category. Let's say this one. So this mean represented the expected phenotypic value for this individual. However, you never see that identical, right? Because of the existence of the measurement error or whatever. So, and we assume this error is following a normal distribution like this. So then that's why we can use this density, normal density or normal probability density function to calculate how well this data will fit this model. Does that make sense to you? All right. So if this individual comes from the case category, so if we simply take the difference between the observed phenotype and the expected phenotype, this will become a residual, right? This will be the residual, and this residual should fit this normal density function very well, and this will increase this probability. Does that make sense? Okay. All right. Now, since we do not know, okay, remember we are dealing a very challenging problem, so we do not know this. Even we knew this is a F2 population, but we do not know the genotype. That for each individual for each individual, we have to guess, right? We have to guess which one, from which of the three category this individual comes from. If we do not know, so we have to evaluate this individual using three different density functions, right? So, and okay, and this probability of this individual actually is a mixture of three normal density functions. Does that make sense too? So this is the mixture probability, and this mixture probability actually for this individual, for specific individual, we have 100 individual, right? Let's say for the 1j equals to 1. So for the first individual, how do we calculate the probability density function for this one? So this probability function is actually a sum of three normal density functions with the weight. So this is the weight, right? Because we knew, yeah, this individual must come from one of the three categories. So that's why we put the weight here, and the weight multiplied by each normal density function, and we make a summation. So this is a sum of the three, and this is called the mixture model. Any questions? Is that clear? And okay, so this is a first step. So for any like statistical model, so if we want to fit our data and estimate the parameters, so we have to calculate the density function, right? Because after we got the density function, we can calculate the likelihood for the entire data. And then once we have the likelihood, we can do the log likelihood like this, and then we can follow our previous norms to do the first. We can do the first derivative of this likelihood, log likelihood, and set this equal to 0. And when we solve this this equation, we can get the estimation of our parameters. So this is the routine we do for statistical modeling. All right. All right, so from here to here, so this is the mixture model density, and this is how we calculate the likelihood for the data, right? So we just multiply all the mixture density for all 100 individuals, for example, 100 individuals, and we just multiply those. But when we do the log, this will be the sum of this log likelihood. And we can handle this log likelihood to estimate the parameters, and also can help us perform a hypothesis testing. All right. So this is just for your information. I don't ask you to write these formulas for me in the exam, because this is difficult and this is hard to memorize, right? So I will not ask you to handle this, but this is for your own information, because if you understand the rationale behind, it will be easy for you to follow my practice code, and now then you can easily understand what is going on there. In the future, when you met with some problem, similar problem in your own research, so maybe you can just change a little bit. Change my code a little bit and use it to handle your own research situation. Okay. All right. Now, the segregation analysis, the reason why we want to use this, because we have some missing variables, right? So here, the eta, maybe this guy is called eta. Okay, eta j is the missing variable, because we do not know, for example, the individual j comes from which subcategory, right? So we treat this one as a missing one. So this is the function of this one. So if the delta, if this individual comes from like the case group, so we will put this equal to K, otherwise 0. 0 indicate like this individual does not come from the K category. This is the missing because we do not know this information. And if this is the indicator variable, we can easily write any observed phenotype. For example, the phenotypic value for the J's individual equals to this plus this plus this, right? This is a mixture. Because if so why is like this? If this J comes from the first group, then only this one equals to 1, and this one equals to 0, and this one equals to 0. So if you simplify this, this is gone, this is gone. Only leaving this and this part, right? So if this is the case, this model can be simplified like this. Right? So if we knew this equals to 1, this equals to 0, this equals to 0. However, we do not know this information. So that's why this is missing, and we use this for model like this. So once we have this setting, so we can easily write the code to estimate this missing values. And this is how the EM algorithm to help us to use the data to calculate the probability of this indicator variables, and help us to eventually achieve the correct classification with this mixture model problem. Right? Okay. And so we have three parameters here. So here we just use the population mean. So this is the expected phenotypic value for the first genotype, the second genotype, and then the third genotype. So I hope I can link this to my example here. So all right, so you see remember that, right? So let me show you. So in this example, I don't know those population means, but this is the true value, and I'm going to show you how I can use this EM algorithm to calculate this. So all right, so in the practice, we just simply implement this to here. So that's the EM algorithm. So EM algorithm successfully converged. Here I ask the program to run less than 100 times, and if the indicate here means like converge, the starting value is 0, means it's not converged. But after the iteration, once it is converged, this will become 1. The indicator will become 1, and the program will stop and give you the value, the solution. So here, as you can see, the iteration, this program actually converged after 33 times iteration. It is converged, and so what does the converge means? Like, so because this is an iteration, so I just compare like the difference between the beta value in the current step and the beta value in the previous step. So I want to see like say like iteration number 10 and the iteration number 11. So in both iteration step, we're going to estimate the beta, right? If in these two adjacent steps, the beta estimation are very close to each other, which means like if you take the difference between the estimation in this step and the previous step, the difference should be very small if it converges, right? I'm gonna see like the maximum difference if this maximum value of the difference is less than 10 to the minus 8. This is a small number, then I'm gonna stop the program because it converges. I'm gonna print out the converge. All right, so as I mentioned, this program converged after the 33 times iteration, and the difference is like this small, see, between the two adjacent iteration. the iteration number 33 and 32. It's very small, so it stopped. And this is the beta estimation. So we estimate 3 betas. Beta 1 equals to 5, beta 2 equals to 10, almost 10, and beta 3 equals to 15. So this is the 3 expected population means for the 3 genotypes. And the sigma is the variance equals to 1. So this is exactly like what I said in the beginning, right? I put the random error variance equals to 1. So this is the sigma equals to 1. Very good estimation. And this is the beta, the intercept, the B0 and the additive and then dominance. So because dominance is almost 0, we don't worry about this. So you can easily calculate the 3 expected a phenotypic value for the 3 genotypes, right? So the 10 minus 5 equals to 5 here. And 10 minus 0 equals to 0 here, equals 10 here. And the 10 plus 5 equals to this 15. So it's beautiful. Okay, so I just want to know, want to show you that. So this beta is the beta I just showed you in the slides, right? Mu1, mu2, and mu3. And there's an association between these 3 beta values and the additive effects and the dominant effects. So I hope you still remember, this is how we calculate the additive effects by using the mid value. So this is the additive effects, which is the A here, right? So we use the where is it? So we used A here. So the additive effects, we put 5 here. So this is very close to the additive effects. And then the dominance effects, just use this, the difference between the heterozygous phenotype and the average of the 2 homozygous phenotypic values. So if you use this, yeah, this value is close to 0. Yeah, it's very good. It's very close to here, right? It's almost like 0. Yeah. Let's see. Oh, okay, no problem, Adrian. All right. So you missed the first part, but it's okay. Fortunately I recorded, so you can watch it later. All right. Any questions here? So I just exactly follow the lecture notes to roll this code over the weekend. And hopefully this, when you run this code, it can help you understand the lecture here. All right, so this is the three mu1, mu2, mu3, right? So this actually are corresponding to like 5, 10, and 15 in my example. So the 3 subpopulation means here. And we use this mixture model here. And okay. Suppose there's no missing value. Suppose if there's no missing value, everything can be observed. So for example, this can be observed. This is not true, okay? But if we assume this can be observed, so it's very simple. We just used the MLE, maximum likelihood estimation, to get the very close, very nice and close solution for this guy and this guy. It's very clear. Unfortunately, we cannot do this because this information is not known, right? So that's why we're gonna use some other strategy to help us solve this problem. Okay, so the EML algorithm. Okay, so if you compare these slides and several following slides with my code, you're gonna see this is exactly what I do in the iteration. So in the iteration, we have 2 steps here, alternate 2 steps. One step is expectation step. So since we have the missing value in the E step, so we just calculate the expectation of this missing based on the previous step, and we replace this expected missing value. We replace the missing value by the expected missing value. Then we treat this missing problem as a non-missing problem. I'm not sure if I made it clear. So initially, this is a missing value problem, right? So we cannot use the simple maximum likelihood estimation to do the estimation. However, if we, in each of this iterative step, if we can calculate the expected value for this missing value from the previous step data information, and then we replace the missing value in the current step by the expected value calculated from the previous step, then we can treat the problem in the current step as a non-missing problem, and then we can use the MLE. So this is the core, the kernel of this EM algorithm. And so in each step, we just calculate the expectation of this missing value and replace the missing value with this expectation, and then we can go to the maximum step to use the maximum likelihood estimation to estimate these parameters for this iteration. And once this step is updated, so we can in the next step, we can estimate the estimation of these parameters, right? We can treat this as a known to go back and calculate the expected value of this missing value again. So we do this again and again until it converged at some point. The converge means like in two adjacent step, let's say 32 iteration and 33 iteration. So in both steps, we're going to estimate this beta, right? And the sigma square. And in this step, we can also estimate the beta and the sigma square. If we want to take a look how close these two estimations are from each other. So if we calculate the difference between these two, the difference is very small, like less than 10 to the minus 8. And the same, when we calculate this two, the difference between these two sigma square estimation from these two adjacent steps, and if this value is extremely small, less than 10 to the minus 8, then we believe the convergence is achieved. So this is a criteria we check whether the iterative algorithm is converged or not. So once this is like this achieved, we're going to stop. And the estimation in the last convergent step will be the final estimation of your parameter. Is that clear? Did I make it clear?
I'll have to read about it.
Yeah. Okay. So this is the kernel for EM algorithm. All right. The one thing is in the final, if I ask you a question, so where and when do we need to use EM algorithm? The first thing is like, okay, we have some missing problem. For some parameters we don't observe. So that's why we want to leverage the EM algorithm, because if we just use the missing value to calculate the MLE, we cannot get a very short and a nice solution. But if we use EM algorithm and in each iterative step, if we replace the missing value with its expectation, then we can treat this missing value problem as a non-missing value problem. Will make the solution easier. So we do this EM iterative analysis until the program converges at some point. Then the final, the estimation from the final step, the convergence step, will be the solution for your problem. Okay. All right. So let me see, what time is it? Okay. Okay, so this is how we calculate expectation. So we want to calculate this, right? We don't know this, so the expectation actually like this. So how can we understand this? So this is actually very straightforward. So because we do not know whether this data point, the first individual came from each category, right? So we just calculate 3 possibilities. So if you look at the denominator, this actually represents the probability from the first genotype, the probability from the second genotype, and the probability of that this individual comes from the third genotype, right? So, and this is the total probability. This is the denominator. Okay, now let's look at the numerator. Numerator is what? Numerator is just the probability from any one category, let's say 1. So if you calculate this, the ratio of this will gives you the posterior probability that how likely this individual, the expectation, or the posterior probability that how likely this individual comes from this group, right? So if this calculation gives you value like 0.9, if you do the same thing, the denominator is the same, but here, if you want to calculate how likely this individual comes from the second population, so this will give you something like very small. And if you do the same thing for the P3, this is calculating what's the chance that this individual came from the third group, right? Do the same thing, but if you calculate this, this will also gives you a very small value. Let's say, what do you think here? So if you calculate this, this will give the expectation of this equals to this, right? Or in another way, so this individual is very likely coming from the first cluster. So this is the expectation step. So what we do here, all right? And in the EM iteration, so we just first randomly or arbitrarily give some initial values for all the parameters of interest here, like mu1, mu2, mu3, and sigma square. And for each iterative step, we have 2 steps, E step and M step. So E step is actually calculate this, and M step is actually use the very nice closed form to get the solution for the parameters of interest. And we just go this on and on until it converges. This is the converging criteria. So we want to evaluate the difference between the estimation from T step and the T+1 step. If the difference is sufficiently small, then means the convergence is achieved. And then the final step estimation will be your solution here. Okay.
Sorry, I might have gotten lost in the annotations, but what should the takeaway message be from this slide?
Say that again. I'm sorry, I cannot hear you very clearly.
Sorry. What should the take-home message be from
here, right? From here. All right. So
yeah,
this part actually is a little bit advanced. So I don't require you fully understand this, but the take-home message from this is like, all right. So that's a good question. So when and how? So because you missed the first part, so let me go back to the beginning. So this is related to the take-home message, takeaway message. So in the past, when we deal with the data with so when we have a data without missing value. So for example, if we can sequencing or genotype each individual, right, the F2 individual for any locus, and if we have the phenotypic value of interest, so we do not need to use this mixture model analysis. We do not need to use the EM algorithm. We just simply use this model to help us test whether additive effects or dominant effects is existing, right? So this is an indication of the association between this locus and the trait. However, today it's different. It's a little bit different. It's challenging. Why? Because we're missing this data. We do not see the genotype data. So that's why we have to use the EM algorithm. So the one of the take-home message for today is like, so when and where we should use this EM algorithm. The answer is like, yeah, if we are dealing with some problem, some missing data problem, then probably EM algorithm is a good solution. It's a good option. So why? Because all right, this slide. Okay, so if we do not have missing problem, if everything is not missing, suppose the missing value were not missing, we can get a very nice close solution for this, right? So we can use our data to immediately get the MLE for these parameters of interest. So here, this is the parameter we want to estimate. This beta, like mu1, mu2, and mu3, we want to estimate this. So if nothing is missing, we can straightforwardly use this MLE to get the solution. Just one step. However, if this problem involves some missing value here, so we cannot do this, right? Because this will not give us this simple solution. It will lead to a very complicated solution, for which you can even you're not able to write code, R code, to calculate those. So this is very complicated. So that's why we want to translate this missing variable, missing data problem into the non-missing problem. How do we do that? So we can do this, we can achieve this by using the EM algorithm. Because in the M step, the maximum likelihood estimation step, we need the non-missing problem, right? So how do we do this? So we can, before we implement the M step, which required the non-missing data, so we can do something in the E step, the expectation step. So we have some missing values in E step, but if we can calculate the expected value of this missing value based on the known information, and then we replace this missing value by its expectation, then we transform this missing problem into the non-missing problem. So we achieve this in the E step. And once we're done with this in the E step, we can go to the M step and totally treat this problem as a non-missing problem and use the closed form to get the simple solution at this step. And once we achieved this in the M step, we can go back to the E step and do this again to calculate the expected value for this missing. And yeah, we just do this iteratively and until it converges. I'm not sure if I made it clear or it's still like complicated.
Yeah, I guess just to kind of make sure I'm clear, we just have to know when to actually use this approach, right? And then how it works iteratively to get the missing values.
Sorry, your microphone is kind of like chopping your voice. Could you?
Oh, sorry. Yeah. Okay, so it's like just so I'm clear, the take-home message is when. Sorry. Okay, I'll compare it.
Yeah, so when do you need to use the EM algorithm, right? Mixture model. Yeah, in the mixture model. So if you have missing data problem, so this is the best way, I think. Does that make sense?
Yeah, that makes more sense. Thank you.
Sure. All right. Okay, so this is the steps we need to use for the EM algorithm. So when you run the code I provided, so you can see clearly. So I just follow the steps to implement this iterative EM algorithm. All right. So once we got this, we can immediately calculate the additive effects and the dominance effects. Any questions here? I just show you in the code, right? So this is how we use this estimated mu1, mu2, and mu3 to calculate the additive effects or dominance effects at this locus. All right, let me stop sharing here and show you this. Okay. Right. So this is the beta estimated from the beta 1, beta 2, and beta 3, or mu1, mu2, and mu3, right? And if you want to estimate the additive effects, so this is just to take the difference between the highest one and the midpoint of the two homozygous individual homozygous genotypes. So that's 5, right? Okay, and the dominance is like this. It's close to 0. So this is very close to what I put in the beginning. All right, and so those are the derivations. So I don't want to like go deeper here. So this this is very complicated. Even for the statistics graduate student, this is very hard. I just quickly go over this with you. So this is not required, but yeah, if you are interested in this, you can spend more time on this. So all right, so the derivation of this EM algorithm. So first we want to see like if there's no missing value, the complete data. So what is the log likelihood function look like? So this is the complete data. However, these are missing, right? So we can easily like replace them in each expectation step. We can replace this missing value using the expected value. So this is how in the EM algorithm we can write the log likelihood function using this formula. All right, just quickly, very quickly go over this. And once we have, so this is what we have learned before, right? So once we have the log likelihood function of your data, so we can take the first derivative in terms of the parameters of interest. And once we got this, we set this guy equals to 0. We can easily get the nice closed solution for beta estimation and the sigma square estimation. So, all right, this is the routine. And see here, so we just set this guy equals to 0, and we can get a very nice closed form to solve this beta here. And then, so how do we prove? How can we prove like using the EM algorithm, the solution will be identical to the solution when we have the complete data? So we need to prove if this equals to this. So this is very complicated. I just quickly go over this with you. So if we just follow this derivative, you can easily show the two things have the same solution here. So all right, So this is the conclusion here. So this derivation shows like the EM algorithm does need to actually get to the identical solution as the MLE if we do not have any missing data, which means like EM algorithm is a good solution to help us get the unbiased solution, even we have the missing value. Okay, now this part is important. In my practice code, you also see I provided a chunk of code to do the hypothesis testing. All right, so here we want to see if there is a segregation between these three genotypes, right? So let me show you. So for example, if this locus, we're still talking about the F2 population, right? If this locus actually is associated with the phenotype, so we should see the segregation, right? Like this. However, if for some locus, let's say B1, 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 B2, this is another locus, and this locus is following Hardy-Weinberg or the proportion of F2. However, if this locus is not relevant to the phenotype of interest, so what if you plot the data, what do you see? You're going to see the mixture together, right? You only see this because you do not see the segregation. Okay, then this will give us two hypotheses here. So the non-hypothesis is actually if this locus is not relevant to the phenotype, we're going to see this distribution, no segregation, right? However, this is the H null. However, if this locus is indeed associated with the phenotype, so we should be able to see a segregation like this. So we can compare this with this to perform a test whether this locus is contributing to the phenotype or not. So this is what we do here. Okay. So this is what we do here. So we want to test whether there's no difference between three groups or there's a difference between the three groups. So we have learned this before, right? So we can use the likelihood ratio test statistic to help us test whether this is true or this is true. All right, so we can easily calculate the likelihood function for the non-model or the alternative model. So this is what we got from the EM algorithm. So if we assume this locus is associated with the phenotype, so we should be able to estimate three different parameters, right? Or mu1, mu2 for the second genotype, or mu3, and they are not equal to each other. So they are not equal to each other. So just like this, okay? However, what is the model if this locus is non-relevant, is irrelevant to this phenotype? So if it is irrelevant, which means like we can only estimate one parameter because they are identical to this, right? So if this is the case, this is the non-model, so we can easily calculate the parameters of these two. We can easily get the estimation for these two parameters here. And using this estimation for these two parameters, given the non-model, we can construct the likelihood for the non-model. And Then we can use the likelihood ratio test to estimate this, and this will gives us the chi-square p-value. All right, so we have talked about this before. I'm going to show you how we use the R code to achieve this. Okay, so when you look at the third block of the practice code, you're going to see I labeled this as the hypothesis testing. All right, so under the NUM model, we just simply estimate the mu and the sigma associated with this mu, and then we can calculate the likelihood for the NUM model, right? So this is very easy. So if you just implement this, it will give you the likelihood for NUM model. This is the likelihood, log likelihood, sorry. All right. And you can do the same thing for the log likelihood for the alternative model. So this will give you something like this. Okay, so this is larger than this one, which means like the data actually is supporting the alternative hypothesis, alternative model rather than the NUM model. All right, following the slides, you can calculate the lambda, which is the chi-square statistic. This is a big one, right? If you use the code here to calculate the p-value, so that this p-value is extremely small, which means you don't believe your NUM hypothesis is true. Or you can say, yeah, this locus actually is contributing to the variability of the phenotype. And the different genotype at this locus is associated with different phenotypic value. So this is something you can use for your future when you do this kind of like missing data problem. All right. And alternatively, you can do like the testing using a more complicated way, but I don't recommend that. So I think the log likelihood ratio test is sufficient good for you. So I'm gonna briefly introduce this to you. This is not required. As we mentioned before, so once we got the first derivative, we can estimate the parameters, right? If we do the second derivative for your model, we can estimate the variance of these parameters. And if we have the variance of the estimation of your parameters, then we can construct the Watt test here. So this is what we do here, right? This is something like the signal to noise ratio. And this is following a Watt test like this. So this is just for your information. Don't worry about this. It's too advanced here. And then you can do the test. And this slide actually shows you the derivation of how we calculate the expected of the second derivative of this, because this is required for calculate the information matrix and subsequent the variance of the estimation. Right. All right.
Sorry, do we have to know the derivative?
Sorry, say that again.
Do we have to know the derivative?
No. Yeah, this is too hard. I mean, this is even, I think this is even hard for the statistic graduate student for their qualified exam. So this is just for your information. Yeah. All right. Okay, for this one, so I hope you just understand this part. So if we want to do the testing, hypothesis testing for the mixture model problem. What we do is like we need to know we can calculate the likelihood for the alternative model, and we can calculate the likelihood for the non-model. And so don't worry about the formulas here. So in the final exam, I will give each of you a data set, and if you, I'm thinking about probably I will give you an open book test because in the past I didn't let my student use so in the past I gave my student a closed book because they do not have to use the code to solve a project. But this time I hope I can give you each of you a different data sets. You can follow the code like this to do the test. So it's easy. You just follow this. But so each of you will get a different data sets. I know the solutions, but you don't know. And you just follow the code here and get the answer and try to explain what the answer means, solution means, and give me the conclusion from this test. So I think this is what I want you to learn. But for the derivation, no, that's too advanced. I don't want to scare you. So this for example, this formulas, you don't worry about this. But you know, you do need to know. So here we use this formula to calculate this, and you know where you can find this code in the practice code, and you just reuse the code to analyze your own data sets and get some results, and put your comments on the results, and let me know if you want to reject your null hypothesis or accept your null hypothesis. What do you think?
Yeah, that sounds good.
All right. So after the class, please spend a little bit of time practicing the assignment. This can help you understand the code and how and when you should use the code to solve your problem. All right. And those part are too hard. And this slide actually shows you like, because the example I gave you is a very straightforward example for F2 population. In F2, we knew the genotype frequency is following like this, right? It's easy. But for some general situation, if the locus is not following this proportions, which means like the proportion of 3 genotypes are unknown. So we have to estimate this genotype proportion as well. So this will even make the situation more complicated. But this is out of our scope, so don't worry. Those slides just for your information. And I think we're done with this chapter. It's a tough one. And I think, so the majority of the theorem I would like to introduce to you in this class are all in the first 10 chapters. So I think maybe in next 2 weeks, in the next 2 weeks, we're going to finish all the theorem parts. When you look at the following chapters, those are some applications of these theorems. So very advanced. So we will not go to the details about those in those later chapters. We're going to probably finish our theoretical parts in 2 weeks, in 2 or 3 weeks. And we're going to finish all the later advanced chapters very quickly. Right now, I would like to remind you of like probably, because for our class, we have 2 parts, right? The final exam takes 50%, and there's a term paper also takes another 50%. So this time I use a little bit different style. So maybe so I will think about the final exam. Maybe I will give you a open book. So because I allow you to use your computer, and I will give you some data sets. Each student will have a different sets, and you're gonna use the code I provided to you in the practice assignment to solve the problem and get the answer. So that's part of your final exam. But now I think maybe it's time for you to think about the term paper. The reason why I believe like the reason you took this class because you think in your future research maybe you need some like statistical method to help you. So I assume probably you have already read some like articles which are relevant to our class. So just find one, identify one paper, interested paper, and read it and try to understand it and prepare a 10 minutes presentation. After the final exam, we're gonna find a time so everybody can present your term paper, and so each student have like 10 to 15 minutes, and followed by 5 minutes like question and answer part session. And I'm gonna give you the score on that part, and so 2 parts add up to your final score, and yeah, I will generate the letter grades based on both parts. So does that make sense?
Yeah, that makes sense. In the meantime, can we run the papers by you to see if it's actually worth presenting?
Oh yeah, definitely, yeah, sure. So so just find your paper and send it to me. So just say, hi, Dr. Jia, does this paper look good for our presentation? Yeah, I will tell you. Yeah, I will give you my opinion. Yeah, usually like students can find a good paper to present in our group presentation. Yeah, don't worry. Yeah, just send me your potential paper. I will give you my opinion. Yeah. All right. So any questions for today? I'm gonna stop here and so answer any questions you may have. I know like this class is actually it's not easy for me to teach, and it's also very hard for students to learn because actually this book is quite hard because it consists a lot of very hard solid statistical theorems. I try to teach this class in a because this is not for statistics department, it's for the biology department. So I try to teach this class in a application way. So I try to avoid the very hard theoretical part, but I try to make it easier for you to understand why this is useful for some biological data, and if we this can help you recognize some problems in your own research, and you know what tools you may use to help you without knowing the details, the advanced part of the method. And for the code practice, so this is the first time I prepare a systematic like practice R code for you. In the past, I just did a little bit, not this much, but hopefully those codes are useful for you. You can keep this for the future use. I hope like some of you can find some of this practice code useful in your future research project. All right, so I'm gonna stop here. So if you have any questions, we can discuss now, yeah, I'm gonna see you next time. Thank you.
Thanks.
Mhm. Stop recording.